In this lesson, we are going to continue our study of random variables. If you know probabilities for all possible values of a random variable, we can determine the mean outcome over the long run. This long run average is called the expected value of the random variable. And it's abbreviated as, or the terminology notation for it is E of x. So think that E of x is the average. The fancy way to say that is E of x equals the Greek letter mu. So the expected value of a random variable x is the mean value of the variable in the sample space of possible outcomes. This is the mean value that you would obtain from an infinite number of observations. So for example, suppose you tossed a coin 100 times and you define the random variable x to be the number of heads on any given toss. Then, the expected value of x, as in how many heads are you going to get out of those 100 tosses, is going to be 50 in the long run. So this calculation, so how you find the expected value or mean value for a discrete random variable, is you take a sum of all the x values times their corresponding probabilities. And you do this over all possible values of the random variable. And another way to write that would be E of capital X equals this sum. Value of x times its probability, where you sum over all the possible x's. And one common application of expected value is to lotteries, and there are great stories of people actually gaming the lottery system using this idea. So here is that idea on a sort of small scale. So there's this person, Mary, and she's playing a game, and the probability that she wins is 0.1, and the probability that she will not win is 0.99. If she wins, she'll be given $100, and if she loses, she must pay $5. If x is the amount of money Mary wins or loses, what is the expected value of x? So let's make this into a table. So x is the amount of money Mary wins or loses. And we're going to have winning be positive money and losing be negative money. So either she wins $100 or she loses $5. And here, the probability of x is the next row. The probability that she wins $100 is 0.01. And the probability that she loses $5 is 0.99. Then the expected value of how much she would expect to win if she played this game an infinite number of times is 100 times 0.01 plus negative 5 times 0.99, which is negative 3.95. So over the long run, Mary loses $3.95 per play. What some people have done when they found out a way to game a lottery system is they compute this expected value sort of in a similar way, and they find that it's positive, which means if you play the lottery a lot of times, you end up winning more than you lose. So there's a really, really great example of this, and we'll try to work it in this semester. So the notation E of x represents the mean or expected value of a random variable x. And this Greek letter that looks kind of like a U, but it's pronounced mu, is used to represent the mean or expected value. In other words, E of x equals mu. Those are the same thing. So you just have to know that those two expressions are mathematically synonymous. So if x is a discrete random variable with possible values x1, x2 up through some number that may or may not be finite, occurring with the corresponding probabilities p1 through something, then the expected value of x is calculated as the mean mu equals e of x, which is the sum of the xi's times the pi's. So the formula says to find the sum of the value times probability over all possible values, which we already said. The probability distribution of the random variable x, which tells us the number of wins in 3 independent plays of a game, for which the chance of winning each game is 0.2, is given in this table. What is the expected value of x? Well, to find e of x, we'll focus on just finding the value in the first part, and then we'll talk about what this means. You take the value of x times the probability, so 0 times 0.512, plus 1 times 0.384, plus 2 times 0.096, and plus 3 times 0.008. And this comes out to be 0.816. So write a sentence that interprets this in these situations. And this is the long run average. So you have to somehow tell me that this is a long run average. So over many repeated, we'll say, trials of playing this game 3 times, the average number of wins per 3 games is 0.816. And some things are important to note here. One thing you really do have to say is that this is a long run average, so that's this whole many repeated trials business. And it does matter that you play the game 3 times, because if it were not 3 times, this table up here would change. So, and also the probability that each game you win a game is 0.2 also does matter, but the point is this is a long run average. Next, we will find a formula for the standard deviation of a discrete random variable. So first recall that in general, what we've seen in the past is the standard deviation of a random variable. This is roughly the spread, or the distance the random variable falls from its mean or expected value over the long run. And similarly here, the standard deviation of a discrete random variable also quantifies the spread of those values, weighted by how likely it is for each value to occur. So here are the formulas for the variance and standard deviation. And remember that the relationship here is that square root of the variance of random variable x is equal to the standard deviation of that random variable x. Now, to find the variance of x, you sum up the differences of the x's minus the mean squared times the corresponding probability. And then to find the standard deviation, you just take the square root of that result. And just note the sum is taken over all possible values of the random variable x. So, for example, first here, let's calculate the mean because we need that to find the variance. So the mean mu is e of x, which is given by value of x times probability. So negative 2 times 0.25 plus 0 times 0.5 plus 2 times 0.25. And this is going to be 0. Now the variance of x, that's the pre-square rooting step. This is the sum of x sub I minus the mean squared times probabilities. So the first x sub I is -2. The mean is 0, so we have -2 minus 0 squared, probability of 0.25, plus 0 minus 0 squared, probability 0.5, plus 2 minus 0 squared, probability 0.25. Well, this gives us 4 times 0.25, which is 1, plus 0, plus 1. So that tells us that sigma squared, which is the variance, is equal to 2. Next, calculate the standard deviation. Well, the standard deviation is just the square root of that variance. So sigma is equal to square root of 2, which approximately is equal to 1.414. Find the expected value for the number of girls in a family with 3 children, assuming that boys and girls are equally likely. Use the probability distribution function given on page 269 of your text. So if we have the first row is number of possible girls. Well, if you have 3 children, you could have no girls, 1 girl, 2 girls, or 3 girls, because we're assuming you have 3 children. And the probability that our random variable x equals a specific number of girls is given by 1/8 for none, 3/8 for 1, 3/8 for 2, and 1/8 for 3. This is a lot like flipping a coin because we assume the probability of having a boy and girl, that those two things are equal. So no girls corresponds to boy, boy, boy. 1 girl could have happened in one of 3 ways: boy, boy, girl, boy, girl, boy, or girl, boy, boy. 2 girls could have happened in 3 ways as well: girl, girl, boy, girl, boy, girl, or boy, girl, girl. And then 3 girls obviously could be, it's 3 girls in a row like this, giving you your 8 total possible outcomes. Okay, now E of x, how many girls would you expect out of 3 births in a long run average? You should be saying 1.5 in your head, but let's verify that. 0 times 1/8, plus 1 times 3/8, plus 2 times 3/8, plus 3 times 1/8. Well, this is 3/8 plus 6/8 plus 3/8, which adds up to 12/8, which is indeed 1.5. So that means in families of 3, or with 3 children, over many families, kind of like the long run, there will be 1.5 girls out of every 3. So insurance companies also know about expected values, and here is one way that they can use them. It's just a very simple example. Suppose the insurance company expects 10% of its policyholders to collect claims of $500 this year, and the remaining 90% to collect no claims. What is the expected value for the amount that they will pay in claims per person? So I'm going to let x equal how much they pay out. And they either pay out $500 or they pay out nothing. I do know that payouts vary, but we'll just say that this is, an average of some sorts. Now the probability that they pay out $500 is 0.1, and the probability that they pay out nothing is 0.9. Now let's find the expected value over many runs. So 500 times 0.1 plus 0 times 0.9 gives you $50 per person. And maybe this is monthly, but this tells you that you should charge more than this to make a profit. But that's how much you're going to expect to pay to each person on average over the long run. Now, some people might collect more and some may collect none at all, but the average per person is $50. So one important family of discrete random variables is called a binomial random variable. So certain conditions must be met for a variable to be considered binomial, but the basic idea is that a binomial random variable is a count of how many times a variable occurs or does not occur in a particular number of independent observations or trials. So the kicker here is that there must be independent observations or trials, and then the bi part in binomial comes from the fact that there are two outcomes. So two outcomes, as in something happens or it doesn't happen. So, for example, the number of wins in 3 games. The two things or two outcomes are that either you win or you don't, and we assume that one trial is independent from one to the next. Or another example could be the number of girls in 6 births. So we assume births are independent and either you're a girl or you're not. Now that's maybe a bit more complicated than that, but the basic idea is that you have two outcomes. So the binomial random variable x is the number of times an event occurs in n what we're going to call trials of a binomial experiment. And n is a number that you fix ahead of time. So in the previous example, we had the number of wins per 3 games. That would be n equals 3. Or the number of girls in 6 births. That would be n equals 6. Now the possible values for x are 0, 1, 2, 3, all the way up to whatever your ending point n is. Okay, before we get there, let's first talk about what describes an experiment. Before we discuss an example, let's talk about what has to happen to have a binomial experiment. So it's defined by the following conditions. First, there are n trials, where n is specified in advance and is not a random value. There are 2 possible outcomes on each trial. The outcomes are called success and failure. These outcomes are independent from one trial to the next. And we also require the probability of success remains the same from one trial to the next. So the success probability is denoted by P, and because you only have two possibilities, as in success or failure, because of the complement rule, failure's probability is 1 minus P for every trial. So here's an example of something that is a binomial random variable, and we will talk about why finding these probabilities is complicated, and I'll show you a formula that you can use to find them all the time. So suppose you have 5 kids. What is the probability that exactly one of them is a boy? Okay, so let's just consider the first case. Well, what if we have a boy and then 4 girls? Okay, well, the probability of that happening is 0.5 to the 5th, because each of our trials is independent. Now, that isn't the only way we could have had one kid being a boy. This probability means, because that B is first, that your boy came first. Your boy could have also come second, could have come third, could have come fourth, or could have been the last. And notice that every single one of these has probability 0.5 to the 5th. So the probability of, we'll say, x equals 1 is equal to 5 times 0.5 to the 5th, which comes out to be 0.15625. Exactly. So first of all, let's talk about why did I say x equals 1 and how come this is binomial. So first of all, let's talk about n, the number of trials. How many trials or times do you have kids? You have 5, so your number of trials is 5. The probability of success would be having a boy. That has probability 0.5. And we care specifically about there being one success or one boy. That's why this was probability x equaled 1. So here is a formula for a more general case. So for a binomial random variable, the probabilities for the possible values of x are given by this formula. Holy moly. Probability x equals some value k is given by this n exclamation mark, which is a super happy number called a factorial. So n factorial over k factorial times n minus k factorial times p to the k, 1 minus p to the n minus k. Okay, first of all, let's just briefly discuss what a factorial is. So, for example, 5 factorial is 5 times 4 times 3 times 2 times 1. 10 factorial is 10 times 9, all the way down to 3, 2, 1. So that's what a factorial is. It's you start with this number and multiply it by every integer number less than it. By definition, not to confuse anybody, but this is just something you're going to have to know, 0 factorial is defined to be 1. So accept it, move on, and work with it. Okay, so we have found the probability that there is exactly k successes. So what I want to just write down here is how the previous example we did is actually the same thing. So in that example, we had n equals 5 trials. We had number of successes, which this is calling k, equal to 1. And our p was equal to 0.5. Now plugging that in, probability that x is equal to 1 is given by this, 5 factorial thing over k factorial, which is 1 factorial. Well, n minus k, 5 minus 1, which is 4 factorial. P to the k, so p is success, that's 0.5 to the first. And then we have 4 failures, 1 minus 0.5 to the 4th. And 1 minus 0.5 is 0.5, so obviously you can see there that we have the whole 0.5 to the 5th bit. Now, how about those factorials? Well, think about them as multiplications. 5, 4, 3, 2, 1. 1 factorial is just 1 times 4, 3, 2, 1. Notice that the 4, 3, 2, 1s cancel. And that gives us 5 times 0.5 to the 5th as we had before. So this first number, this n over bunches of factorial stuff, tells you the number of simple events in the sample space that had exactly k successes. So for us in that previous example, that was kind of like the places the boy could have fallen, and it could have fallen in 5 different places. You can imagine if you had 2 boys, there might be more outcomes, and finding all of those and listing them might be kind of complicated. This second part gives the probability for each of the simple events which x equals k. So if x equals k, there are k successes. That's why this is p to the k power. And there are n minus k failures. That's why this is 1 minus p. That's the failure probability. N minus k. And if you think about it, you have k plus n minus k equals n, as in the exponents. And this is your total number of trials. Okay, so we're going to actually use that formula. We'll talk about how to work through it. I know it's complicated, but put it on a note sheet for your next exam. Okay, for each of the following binomial random variables, specify n and p. Remember that n is the number of trials, and p is the probability of success. So a company puts a game card in each box of cereal, and 1 out of 100 of them are winners. You buy 10 boxes of cereals, and the random variable of x is the number of times you win. Now we do assume that from one box to the next the boxes are independent, as in they don't put all of the winning boxes in one crate. Anyhow, first of all, n, the number of trials. How many boxes of cereals do you buy? You buy 10, so n is equal to 10. Which means you can win 0, 1, 2, 3, up to 10 times. And the probability of success, we're going to define success as winning. It is 1 out of 100, or 0.01. So Jack likes to play computer solitaire, and he wins about 30% of the time. If x is equal to the number of games he wins out of his next 20 games, what is n and what is p? Well, the number of times he tries is 20. And his probability of success, since he wins 30% of the time, is 0.3. Suppose that in a very large population, 10% of individuals are left-handed. We're going to sample 5 individuals, and x is the number of left-handed individuals among those 5 people. Find probabilities for the following events. We'll do these by hand, but I'm also going to tell you how you can use software to check your answer. Okay, so before we start, let's find our n and our p. So our number of trials is 5, because we talk about 5 people. And if success is finding a lefty, that happens with probability 0.1. Okay, the probability that exactly one of the individuals is left-handed. That's the probability that x is equal to 1. So remember our formula, probability that x is equal to a k is n factorial over k factorial, and minus k factorial, p to the k, 1 minus p to the n minus k. So we're going to be using that. Okay, so n is 5, so you have 5 factorial over 1 factorial times 4 factorial, 0.1, that's our success. We have 1 success, which means we have 9 failures, or sorry, 4 failures, and 1 minus 0.1 is 0.9, 0.9 to the 4th. Together, these exponents should add to the number of trials you have. Let's simplify that. So 5 factorial is 5, 4, 3, 2, 1. 1 factorial is 1, then 4, 3, 2, 1. 0.1 and 0.9 to the 4th. Notice that the 4, 3, 2, 1s cancel. We have 5 times 0.1 times 0.9 to the 4th, which comes out to be about 0.328 approximately. So in Excel, that's how I'm going to show you how to check them. If you're using a different kind of software, that's totally fine. What you do is you enter a cell and you push equal and type in this thing called binom dist, which stands for binomial distribution. And the order of stuff, it'll tell you this if you start to put it in, it'll kind of prompt you as to what's needed. You have K, N, P, and then you have a true, false command. So for this example, we type in binom dist, and that command might be different if you have slightly different software. So if you do, ask. Okay, K would be 1, N would be 5, P would be 0.1, and this true, false. So true corresponds to a cumulative distribution function and figures out the chances that something is less than or equal to that. And false does just probability that x equals that k specifically. So in this case, you would put in false. And you can verify for yourself that this gets you the same answer. So at most, one of the 5 individuals is left-handed. So that means 1 is the most number of lefties we can have. This is the probability that x is less than or equal to 1. And you have to think, well, x can equal 0, 1, 2, 3, 4, or 5 left-handed people in your sample. Now the ways that x can be less than or equal to 1 is either x can be 0, or x could be 1. We found this one in the previous example. So let's just work on finding this one, x equals 0, and then we'll go from there. So remember, we have n factorial, which is 5, over k factorial, which in this case is 0. N minus k, 5 minus 0 is still 5. 0.1 to the 0 times 0.9 to the 5th. So a couple things you have to believe first. 0 factorial is 1. Something to the 0 power is also equal to 1. So this ends up giving us 0.9 to the 5th power. And that should make sense, because if you have no lefties, that's probability of having a righty, a righty, a righty, a righty, and a righty, each with corresponding probability 0.9. So this comes out to be approximately 0.590. So probability that x is less than or equal to 1 is equal to 0.590 plus 0.328, which is 0.918 approximately. And to put this into Excel, just if you want to check your work, So doing less than or equal to 1 will change that last command. So we're still going to do binom dist. So first comes k, which is still 1. Next comes n, which is still 5. Then the p is still 0.1, but we say true here. And that true will tell it to do what's called the CDF, which we discussed in an earlier lesson. And that does this whole x less than or equal to a specific number. And then finally, what is the probability that 2 or more of the individuals are left-handed? So that means x bigger than or equal to 2. And thinking, well, our x could be 0, 1, 2, 3, 4, 5. This would be a probability that x is equal to 2, plus probability that x equals 3, plus probability that x equals 4, plus probability that x equals 5. And before you freak out and don't do that, think about it this way. 2, 3, 4, 5, those are all these events, which is the opposite or the complement of the events 0 and 1. This is the same thing as 1 minus probability that x is equal to 0 plus the probability that x is equal to 1. And this we found in example A or B. And so if you're clever, you should use this trick. So that's 1 minus 0.918, which comes out to 0.082. Okay, suppose you have a 15-question true-false quiz. You have not studied, and you have to guess on every question. What is the probability that you will pass with at least 10 correct answers by guessing alone? You're allowed to use software to compute probabilities here. So first, this is a binomial random variable. The number of trials is 15. And the probability of success is 0.5. We're looking for the probability that x is bigger than or equal to 10 because we need 10 or more correct answers. Now, statistical software is only going to do inequalities in one direction, and that direction is almost always less than or equal to. So you have to make this into a complement. And now think the event 10 and up means you got 10, 11, 12, 13, 14, or 15 of them, right? That's the opposite of, or the complement of, having less than 9, correct? Okay, so in Excel, or something like that, I'm going to find the probability that x is less than or equal to 9. And that is binom dist, that's the command. First is k, which is 9. Next is n, which is 15. Next is p, which is 0.5. And then we say true because we want to do the CDF. And this is 0.84191. And before you get excited, you're like, woohoo, not studying for my next quiz, don't forget that this is the complement of the event you want. So it's the event that you get less than 9 question rights, which happens all the time. Bummer. So probability that x is bigger than or equal to 10 is 1 minus this number, which is 0.1509. So the moral of the story is you should study some. Now finally, we're going to find the expected values mean and standard deviation for a binomial random variable. So the mean, mu, is just given by NP. So number of trials times probability of success. And if you go back and look at some earlier examples, like example 2a and example 4, you'll find that those things were binomial, and you could use this to find the mean instead of the other definition we did. And the standard deviation is given by root np times 1 minus p. And similarly, you can use this to find the standard deviation for something that you know is binomial. We didn't do any examples of that, but you can. So suppose a fair coin is flipped 200 times. The random variable x is the number of heads out of the 200 tosses. So is this a binomial random variable? If so, specify n and p. So yes, we have two outcomes, as in heads or tails, and we also do need to assume the trials are independent. Okay, and assuming those two things are true, n is equal to 200, p is equal to 0.5. Okay, mu, e of x. Well, this is np, or 200 times 0.5, which is 100. And that should make sense. If you flip a coin 200 times, you'd expect 100 of them to be heads. And that's not going to happen every single time, but that would be kind of like your long-run average per 200 trials. So, and then finally, standard deviation, or sigma. This is root np times 1 minus p. So this is square root of 200 times 0.5 times 0.5, which comes out to be 7.071 approximately. And that tells you what the variability will be in your trials of 200. So using your, pretend this is about equal to 7, let's say, using your empirical rule, 68% of the time, you're going to have between 93 and 107 heads per 200 tosses. 95% of the time, you're going to be between, so 93 minus another 7 would give us 86 to 114. And that will be the number of heads per 200 tosses. And similarly, you could find the almost everybody, 99.7, will be between, on the upper end, 121, and on the lower end, 79. So if you do 200 trials, this tells you kind of what the range of number of heads you'd expect to see. There'll be some variability, but it'll be centered around that 100, which seems like the most logical average. I do understand that binomial random variables are pretty challenging, so in the next lesson, whenever we have some spare time, we'll do another example just to help you review.